Hey everybody, Mr. Murray here, back on Mr. Murray's Mathland, and today we are talking about finding holes in rational functions as well as vertical asymptotes. But we've covered vertical asymptotes in an earlier video, and just to get the idea across, they're both places, holes and vertical asymptotes are both ways that the graph is undefined, but they're completely different looking things. A vertical asymptote is when the graph is completely disrupted like this, and a hole is when you have something like essentially a single point has been removed from the curve, but otherwise it is completely undisturbed. So a vertical asymptote is always x equals some constant, but a hole has an x and a y coordinate. And so we're talking about finding the coordinates of those holes and distinguishing when something is a vertical asymptote as opposed to a hole, or vice versa. Because as I said, they're both places where the graph is undefined, and that's going to come from when the fraction is undefined or when the denominator is 0. So first things first here, let's factor this denominator. This is a nice difference of two squares, x plus 5, x minus 5. So you can see right off the bat that this graph is undefined. This function is undefined whenever x is equal to 5 or negative 5. So those are what I would call excluded x values from the domain. However, they could either both be vertical asymptotes, both be holes, or 1 and 1. And the way we tell is we have to see, do either of these factors cancel from the denominator? And so to do that, we have to look at what's in the numerator along with it. So in the numerator, we can factor that to 2 times x minus 5. So here's what we're looking at. I'm just writing out a neater version of it. And you can see that the x minus 5 cancels. In other words, I was able to remove that quantity of x minus 5. And so that quantity of x minus 5, which had an excluded, a solution of x equals 5, that's going to be a hole. When you're able to remove it or cancel it from the denominator entirely, that's when you're just like removing a point from the curve. Anything that's still in the denominator, it's still making it undefined. That's what we call a non-removable discontinuity. That is still going to be a vertical asymptote. So what we have here is the solution to what's still left over in the denominator. In this case, x equals negative 5. That is a vertical asymptote. The hole, however, as we said, at this x value of 5, which came from this x minus 5, which canceled, there's going to be a hole. But we need to find the y coordinate of that hole. And so how do we find the y coordinate that goes with an x value? Well, you plug it into the function. And now that that x minus 5 is canceled, you can plug 5 into the reduced function and it won't be undefined anymore. So I'm going to plug 5, the x value, into the reduced function, and that's going to give you 2 over 10, or 1/5. So our vertical asymptote is at x equals negative 5, and our hole is at 5, 1/5. Okay, so quick recap there. If you can cancel the quantity from the denominator, that means you're going to have a hole at that x value. And to find the y coordinate of that hole, just take that point and plug it in to the function after you've canceled it away. Anything that's still in the denominator, that's going to be a vertical asymptote. Its graph's undefined there and it's not going anywhere. Let's just take a look at a couple more examples, but that's the gist of it right there. So let's factor numerator and denominator and see. denominator is where I'm going to get those potential holes from, those excluded x values. So I'm going to factor this to x minus 10 times x plus 2, right? Well, it multiplies to negative 20 and adds up to negative 8. And up top, what multiplies to 14 and adds up to 9, that would be positive 7 and positive 2. So right off the bat, you can see that excluded x values are 10 and negative 2, two things that make the denominator 0. Now you can see, are either of those or both of those going to cancel? The x plus 2 is going to cancel. That means this one is going to be a whole. The thing I'm left with thing that's still making it undefined, which is the 10 in this case, that's going to be a vertical asymptote. So vertical asymptote, we're really done with that. It's x equals 10. The whole is going to be a whole at negative 2, comma, what? You got to find that y value, and to get that y value, you're just going to plug in the x value of negative 2, right? And you got to plug it into the reduced function. So negative 2 plus 7 over negative 2 minus 10. That's going to give you 5 over negative 12, or negative 5/12. And there we go. Two places where the graph is undefined. A whole is what's called a removable discontinuity because we're able to remove it. And this one, a vertical asymptote, is called a non-removable because we couldn't remove it. And one more example here. And of course, for all these, you could also find all kinds of fun things like horizontal asymptotes and zeros and y-intercepts, and that will help you draw the graph. But we're just focusing on how to find holes in vertical asymptotes today. So our denominator factors to x plus 1 times x plus 1, or x plus 1 squared. So there's only one excluded x value right now, and that would be x is negative 1. Up top, what multiplies to negative 6 but adds up to negative 5, negative 6, and positive 1. So you can see x plus 1 cancels. However, you're still left with x plus 1 in the denominator. So when this happens, and that's intentional why I included this example, even though I was able to cancel one of the x plus 1s, I'm still left with x plus 1 in the denominator. That means this is still making the graph undefined. It's a vertical asymptote. So it'll only be a whole if you can completely get rid of that, whatever that quantity is. This is making equal to 0. So this one has a vertical asymptote at x equals negative 1. And since there's no other quantity that I was able to cancel, that means there are no holes in this graph. Not every graph is going to have a hole or a vertical asymptote. So know when to tell the difference. Okay, kids, that's it for today. If you got any questions, let me know.